All right, so our next activity is to figure out a floor beam design, and we're specifically going to talk about a wide flange beam. With these beams, there's a few more checks involved to make sure that they're strong enough to support your load. All right, so some background knowledge, things that we need to know. So what is a beam? We talked about it a little bit. Pretty much it's a horizontal support structure that can support a load that's being pressed on it. So it might be an I-beam, it might be an open steel web joist, it could be a floor joist or a girder. So there's different names for it. So that's what a beam is. Then forces that act on the beam, there's two big ones that we talk about. One of them is when your beam connects to, say, a column, there's a shear force that makes those two kind of want to slip against one another. That's a shear force, and you can see that here, where you have kind of two forces that are kind of pushing and sliding past each other. That's what they want to do. Obviously, we're going to make a connection so they're strong enough so that they don't slip, but that's what they want to do. That's a shear force. And then a bending moment is the force that's applied to the actual beam on top that makes it want to bend, okay? And you can see that in the diagram there. That's the blue arrows. It makes it want to bend. Another term that we need to know is compression and tension. So when you have a beam and you put a load and it's causing it to bend, there's two things that are happening. The top of the beam is in compression, it's pushing towards each other, and the bottom of the beam is in tension, it's pulling apart. So another way to think about these words is in PE class when you're doing a stretch, maybe you're doing this stretch, this side of your body, right, that's squished together, that's in compression, right? As opposed to this side that you're actually trying to stretch, it's in tension, it's pulling apart. That's why you feel that stretch in your muscle, because your muscle is trying to pull apart, where all your muscles over here are bunched together. So that's the same idea, compression and tension. And one of the last terms that we need to know and check for in our beam design is, hey, is our beam being deflected too much? And deflected is the distance from when our beam is flat, and then when you fully load it, it's going to deflect a little bit, it'll bend a little bit. The deflection is the distance from where it starts to where it ends with the deflection. So you have to make sure that your beam isn't maybe deflecting a foot, right? That's obviously an over-exaggeration, but you don't want your beam to bend a foot down because then whatever's below that, maybe a wall will crack or a dry wall, you don't want it to deflect too much, okay? And that's what we have to design for. All right, so some background knowledge about beams. These are formulas that we're not really going to use, but I want to make you aware of them because on your end of a course assessment it might pop up. So you might see these, you see these formulas on your formula sheet. So I just want to make you aware of them, kind of explain them a little bit, and then move on. So you will see them on your formula sheet: stress, strain, and the modulus of elasticity. So stress is the measure of magnitude on the internal forces acting between the particles. So it's the makeup, the materials inside this beam, the forces acting against each other, that's the stress on the actual beam, kind of what's going on inside. And the equation is F over A. Then there's axial stress. So with tension and compression, when things are wanting to pull apart. So when I bend this beam and right down here, it wants to really pull apart. At that part where it wants to pull, there's axial stress on that, okay? And that has its own equation, as you see here. And then there's also strain. So when you're changing shape of a material caused by an external force. So this happens actually a lot in rebar. When we place rebar in concrete, it gets stretched. So they actually stretch it. They put an axial strain on it. They stretch the rebar. They pour the concrete, let it harden, and then they actually release that rebar. And that's actually a post-tension floor, which is kind of cool. So that's kind of what axial strain is when you pull it apart. Strain that is on that material. Again, want to make you note of them. We don't really talk about them a lot, but in case there was a question to come up, you know where it is in your formula sheet and kind of what they are about. So thinking about a beam, there is a diagram that kind of tells us at what point does our beam fail, right? Because we don't want our buildings to fall down. So every kind of material has a different point of failing, okay? And we always want to keep our design, we always want our beam within the elastic range. So what that means is, okay, when I put a load on my beam, right, so I drive a car on top of this beam, it might deflect a little bit, might bend a little bit, that's okay. But as soon as that car drives away, that beam pops straight up and it's straight again. It's elastic, it can bounce back, right? Kind of like your skin, it's elastic, it stretches. So that's where we always want our beam to be within. But sometimes it hits a certain point over time or the amount of weight that's put on it, and it gets in this plastic range where it just can't bounce back, okay? So after that really heavy semi-truck sits on this beam, and once that semi-truck leaves, that beam is not going back to straight. It is now permanently kind of bent in a little bit, okay? And so beams show signs from going from elastic where it kind of just keeps bouncing back, it's great, over time and maybe too much heavy loading on it. It might have some deformities to it, and then there's always this point where you hit a fracture, and that's when it actually breaks, and that's when we get failures and buildings collapse per se. So those are kind of the three different ranges that materials go through. And we study those ranges, and we always, when we design as a civil engineer, we design our beams to always stay within this elastic range, always. So we really focus on how much weight is going to be on it, how long is it going to be on the building, and we make sure to design that beam so it never has to cross over into that plastic zone. Meaning that we know, we always over design. So if we know, hey, this is a warehouse in the future, there might be semi-trucks in here, then we're going to over design and make sure that it can hold that so that it never hits that plastic range. Okay, it can always bounce back. All right, how do we select what steel beam we should use? So there's a lot of different criteria, and there's a million different sizes of these types of beams. There's tables and tables. It's actually a whole book full of different sizes that you can choose for these beams. So one of the things that helps us decide what size to use is called our plastic section modulus, which is known as ZX. And pretty much that's how much resistance to bending a shape has when positioned a specific way. So the great example is just this beam itself. So when I bend it, see how I'm trying to bend it in this direction, right? I'm trying to bend it in half here. It's really, really hard. It might not look like it, but it's really hard to bend it. I can't really go any further than this. As opposed to if I looked at my beam in the other section direction, okay? So instead of this direction, I'm looking at it in this direction. So maybe I use my beam this way. If I put a load in the middle, look at how easy it is for it to bend. Okay, so there's different section moduluses that we look at as how strong is a material in a certain direction when it's loaded. So when this material is loaded this direction, it's really hard to bend it. As opposed to in this direction, if I put a load on it, it is very easy to bend. So that's a plastic section modulus, and we just look at how easy or hard it is to bend different materials looking at different axes.